Welcome to The Explainer. Today we are unpacking a VC pitch document that honestly reads straight out of a sci-fi novel. But the crazy part? It is entirely real. We're going to dive into a portfolio called Imagenta, and we'll see exactly how they are using nanophotonics and quantum mechanics to completely replace physical moving parts across our major global industries. We're talking about literally stripping out the mechanical gears, the spinning motors, and the fragile lenses that currently run our world, and replacing the whole shebang entirely with light.
All right, let's cut through the noise for a second. This idea right here captures the entire thesis of what we're looking at today. Think about it. We have this incredible algorithmic intelligence, AI, machine learning, global data networks, but it's all trapped. Our modern digital economy is entirely bottlenecked by legacy mechanical hardware. We're basically trying to run the software of the future on hardware that still relies on physical motion. And motion means it generates heat, it suffers from massive latency, and eventually it just breaks down. Imagenta's portfolio is laser-focused on breaking that exact physical bottleneck.
So, to understand how they plan to pull this off, here is our roadmap for today. We'll start with the photonic paradigm shift, then look at how it revolutionizes computing and storage, move into inertia-free medical innovation, explore manufacturing and mobility, and finally, break down that massive trillion-dollar market valuation.
Section 1. The photonic paradigm shift. Moving beyond mechanical limits.
Okay, so I want you to think of mechanical moving parts as the ultimate villain in our tech story today. Whenever something physically moves, you get friction, heat, wear and tear, and inevitably failure. The hero here is solid-state optical hardware, and it's driven by something called two-photon absorption. This is a nonlinear process where two low-energy photons are simultaneously absorbed to excite a molecule. Normally, a standard laser beam just affects everything along its path, right? But with two-photon absorption, a reaction only happens at the exact infinitesimal point where two specific beams intersect. This gives you pinpoint, nanoscale precision deep inside a material, completely bypassing and ignoring the surrounding area. It's an absolute game changer. And this brings us to the unifying philosophy across all 15 of Imagenta's disparate technologies, the inertia-free motif. Everything is solid state, no moving parts. This means you get total immunity to mechanical wear, zero physical vibration, and zero mechanical latency. You are operating, literally, at the speed of light, entirely without friction.
Section 2. Revolutionizing computing and storage. Erasing the heat and data bottlenecks.
We all know AI and cloud computing are just exploding right now, but they're hitting a massive physical wall of heat and power constraints. Just think about our current legacy hard drives, fragile, spinning magnetic platters that easily break down. While Imagenta's answer is lanthanide-doped glass blocks. Imagine a solid, transparent block of glass embedded with luminescent nanoparticles. Using that two-photon absorption we just talked about, data isn't written on a spinning disk anymore. Instead, it's suspended as glowing voxels in hundreds of vertical layers inside the glass. No moving parts whatsoever, completely bypassing the diffraction limit of standard light.
This simple shift is huge. We're talking about an up to 95% reduction in data center electricity usage. 95%. Because it's solid glass, it requires near-zero energy to preserve the data, a concept they call cold storage. Plus, it's immune to water damage, totally immune to temperature fluctuations, and boasts a lifespan of centuries. It radically shrinks the massive real estate and power demands of our modern data centers.
But it's not just about the storage, it's the actual computing. Current AI systems are literally choking on the heat generated by pushing electrons around electronic logic gates, which are super constrained by memory bandwidth limits. Imagenta swaps that out entirely for interference-based optical compute engines. So instead of electricity, they use structured light beams. The computation actually happens through optical interference patterns. Complex mathematical results emerge directly from the light waves propagating and interacting in space. It gives you infinite bandwidth, parallel processing, and a massive reduction in cooling costs.
Section 3. Inertia-free medical innovation. Non-invasive healing.
Let's pivot to healthcare for a minute. This is an industry where physical movement inherently causes trauma. Whether it's the bulky scanning hardware or the actual act of surgery itself, motion means incredible strain, time delays, and tissue damage. We are finally shifting from invasive, tissue-damaging inpatient surgeries to outpatient light-based cellular disruption. By using multi-photon targeting, delivering energy only at a precise internal focal point without actually cutting the skin, hospitals can provide non-invasive deep tissue therapies. This converts complex, painful, inpatient procedures into fast, sterile, outpatient appointments. Let's look at how they build their imaging and surgical navigation hardware, because this is just fascinating. They use something called acousto-optic deflectors, or AODs. Here's how it works. Step 1. High-frequency RF acoustic waves propagate through a solid-state tellurium dioxide crystal. Step 2. This creates a dynamic periodic density variation, so think of it kind of like an instantly shifting prism. And Step 3. This allows the surgical laser focal point to literally snap to random regions of interest within a 3D volume of tissue. It completely bypasses those slow, motorized lenses, instantly adjusting focal depth to compensate for something as subtle as a patient taking a breath during robotic surgery.
And the speed of this? It is staggering. We are looking at instantaneous switching rates of up to 100 kilohertz. By combining these crystals in specific configurations, they achieve simultaneous, microsecond-level volumetric scanning. This feeds robotic surgical platforms with real-time, aberration-free microscopy data that is fundamentally faster than any mechanical motor could ever achieve. And for treatment planning, they've developed 2-photon holographic radiotherapy simulators. Just imagine a transparent cube filled with highly luminescent quantum dots. Intersecting infrared lasers sweep through the volume, instantly emitting visible photons exactly where they cross. It physically visualizes a glowing, true 3D, holographic heat map of a patient's planned radiation dose. This isn't just a cool 3D visual, it completely automates an agonizingly complex workflow, perfectly spares healthy organs, and relieves a massive global shortage of medical physicists.
Section 4. Manufacturing and Mobility Reimagined. Shaping the Physical World.
Taking this tech into the physical economy, if you've ever seen autonomous vehicles testing on the road, you've definitely seen those bulky, spinning LiDAR scanners on the roof. They are fragile, they suffer from constant mechanical wear, and vibrational disruptions easily ruin them. Now consider the alternative. Microscopic KTN crystal chips. These are potassium tantalite neobate crystals sandwiched right between electrodes. When a voltage is applied, the crystal instantaneously alters its internal refractive index, bending the infrared laser beam with absolutely zero physical movement. It's solid-state, highly durable, and it radically reduces replacement costs for automakers.
And that exact same bottleneck applies to modern manufacturing. Traditional 3D printing is agonizingly slow, tracing layer by layer like a snail. Imagenta uses volumetric triplet fusion instead. Multiple infrared laser beams intersect inside a vat of liquid resin. The cumulative light intensity triggers a photochemical collision, instantly curing the resin. The result? Entire 3D objects are formed simultaneously inside the volume at millions of voxels per second, completely bypassing physical layering. It's like it just materializes out of thin air.
The bottom line here is sheer economic impact. We're talking about an up to 70% reduction in production costs. By swapping out massively expensive ultra-fast femtosecond lasers for simple arrays of low-power diode lasers, the hardware costs are radically reduced. You go from a slow, expensive mechanical process to a continuous, near-instantaneous optical one.
Section 5. The trillion-dollar market. Valuing the photonic shift. Now, I know this tech sounds like pure sci-fi, but their VC financial model is incredibly grounded in reality. What's so compelling here is that they actively reject hyperinflated monopoly projections. Instead, they rely on a highly defensible 3 to 5% baseline penetration for most of their assets. They only stretch that model to 10 or 15% for foundational hardware that solves definitive legacy bottlenecks, like the solid-state LiDAR for autonomous vehicles or the optical glass for cloud storage.
When you step back and look at the sheer scale of these interconnected markets, it's absolutely breathtaking. You have legacy behemoths like global autonomous vehicles and global cloud computing taking up massive chunks of the global economy. But then you also have smaller yet absolutely critical foundational tech like the quantum internet backbone and telecommunications. By injecting inertia-free solid-state solutions into every single one of these sectors, the portfolio captures immense value across interconnected global industries.
And that leads us to this mind-boggling number, 1.76 trillion pounds. That is the estimated total annual recurring revenue for the entire Imagenta portfolio modeled out to 2035. By solving fundamental physical barriers, by stripping out the friction, the heat, and the mechanical wear of the 20th century, this portfolio bridges the gap between deep tech physical potential and commercial reality. And as we can see, that leads to an immense valuation.
So I want to leave you with this provocative final thought, echoing the very thesis of the document we've explored today.
If the physical friction of moving parts is exactly what's holding back our digital and algorithmic potential, when light completely replaces motion, exactly how fast will the global economy accelerate? Thank you for joining me on this explainer, and I'll catch you in the next one.